We've explored various techniques that we can use to calculate the derivative of a function at a specific x value. In other words, we can determine the slope of the line created by the function at any point on the line. Now, this ability to calculate the slope means that we can use derivatives to determine some interesting properties of the function. Let's examine this function, in which f of x is x squared. Now, here's the graph of that function. The graph shows that initially, as x is increasing, the value of the function is decreasing, but the tangent lines are getting progressively less steep as the rate of change slows. At this point, the graph bottoms out, and we reach the minimum value of the function. And the tangent line shows that the rate of change here is 0. The line is neither increasing nor decreasing at the minimum point. Then the function starts to go up again, and the tangent lines get steeper, showing an increasing rate of change. Now, using the power rule, we can easily calculate the derivative for this function as 2x to the power of 1, which is just 2x. And this looks like this when graphed. Now let's see if we can find a relationship between the derivative function line and the line for the function itself. When the function is reducing in value, the derivative is negative, indicating a downward slope. Additionally, the derivative is getting closer to 0, reflecting the fact that the rate of change is slowing, and it's a straight line indicating that the slope is decreasing at a constant rate. At the point where the function graph reaches the minimum point where it stops decreasing before starting to increase, the derivative line crosses 0, indicating a flat slope or no change. Then as the function starts to increase again, and the rate of change is accelerating, the derivative at this point is positive, indicating an upward slope, and it's increasing, indicating that the slope is steepening. Here's another function and its derivative. And here's the graph for both. Now this time, the function is initially increasing, but the slope is becoming less steep as x increases. The derivative is therefore positive, indicating a rising function value, but it's decreasing, indicating that the rate of positive change in the function is reducing. When the function reaches its maximum, where it stops increasing before it starts to decrease, the derivative crosses 0, indicating no change in the slope at that point. Then, when the function starts to fall, the derivative is negative, to tell us that the function is decreasing, and it's moving further from 0 to indicate that the rate of change is getting steeper. Alright, let's look at one more function and its derivative. And here's the graph for both. This time, the function is increasing with the slope becoming less steep. And as expected, the derivative at these points is positive because the function is increasing. The derivative is also reducing because the rate of the slope is getting shallower, but this time, the rate at which the slope is shallowing is itself changing as the function gets closer to flattening out. The function then flattens out to create this saddle-like shape, and at this inflection point, the derivative is 0. Then our function starts to increase again at an increasing rate, and at these points, the derivative returns to being positive and curves to indicate an increase in the rate of change for the function. So a key takeaway from these three examples is that something interesting is happening to the function whenever the value of the derivative is 0, and we call these critical points. If the derivative has a constant value of 0, then the function has a constant value with no slope. If the derivative passes through 0 from positive to negative, then the function has a change of direction from upward to downward, indicating a peak or a local maximum. Conversely, if the derivative passes through 0 from negative to positive, then the function has changed direction from downward to upward, indicating a trough or a local minimum. And if the derivative touches 0 without passing through it, then the function has an inflection point where it flattens out and then resumes changing in the same direction.